Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for game of life problem. Let's look at the problem description. We are given a board which is made up of m by n grid of cells where each cell have an initial state, either it is live with value 1 or dead represented by value 0. Okay, and each cell interacts with its 8 neighbors horizontally, vertically and diagonally using the following 4 rules. So any live cell with fewer than 2 live neighbors dies, and any live cell with 2 or 3 live neighbors lives on to the next generation, and any live cell with more than 3 live neighbors dies, and any dead cell with exactly 3 live neighbors becomes a live cell. The next state of the board is determined by applying the above rules simultaneously to every cells in the current state of m by n grid board. So in this process, births and deaths occur simultaneously. And given the current state of the board, we have to update this board to reflect its next state. So let's take a look at the example 1. So in this case, for this cell, there are only one live neighbor. So this remains in the dead state. And when we process this cell, there are only one live neighbor. So this is dead, this is dead, this is dead, this is dead. Only this is alive. So this cell will die. So that's why the value is 0. For this cell, there are 2 neighbors alive. So it changed from dead to alive. And for this cell, there is only one live neighbor. So it will change from alive to dead. So that's why it is 0. And for this cell, the number of live neighbors is 3. So it becomes alive from dead. So in the case of example 2, so this cell has 2 live neighbor, and this cell has 2 live neighbor, and this cell has 2 live neighbor. So that's why they remain alive. But for this cell, there are 3 alive neighbors. So it's changed from dead to alive. So the constraint for this problem are m is the number of rows in the board, n is the number of columns in the board. So the value of m and n is ranging from 1 to 25. The value of the cell in the board is either 0 or 1. And we are expected to solve this in place. We are given a board with 4 by 3 grid of cells, and that all the cells next state will be 0 0 1 0 1 0 1 1 0 1 0. So the current cell state will be changed based on these rules. For any given live cell, if it has less than 2 live neighbors or greater than 3 live neighbors, it will become dead cell. It will move to a dead state. If the live cell has exactly 2 live neighbors or 3 live neighbors, then it will continue to be alive. And if any dead cell with exactly 3 live neighbors, then it will become alive. So we have to apply these rules for each cell. But programmatically, we can process this cell only after processing this cell. So if we change this state, when we try to compute the state for this cell, the previous state is lost. And also we are expected to solve this problem in place without allocating any additional space. So in order to solve this with constant space, we need 2 additional state to be stored in the cell. Whenever a cell is changed from dead to alive, we need a unique state value for that. And also when a cell is moved from alive to dead state, then we need to have a different state value. So 0 is for dead, 1 is for live, and 2 is for live to dead, and 3 is for dead to live. So there are 4 states we need to maintain. So now we have 4 possible states for each cell. Okay. So next step will be we will have to traverse each cell and apply this rule and then update the state of each cell accordingly. For example, when we process this cell 1, this cell has only one live neighbor. Okay. then this cell become dead. So we have to set value 2 to this cell, okay, because this cell is changed from live to dead, okay. So when we compute this cell's state, we have to check whether the neighbor's value is either live or live to dead. If either one of them is true, that means neighbor cell is alive. And if the cell is changed from dead to live, then we have to set value 3 for that cell. See, this is the initial state of the cells in the board, and when we process this cell, it has only one live neighbor, so it changed from live to dead, okay. So that's why we set the value 2 for that cell. Next, when we compute the next state for this cell, we check whether the neighbor's state is 1 or 2. That means this cell was alive earlier, so we can account the cell which is in the alive to dead state also alive with respect to this cell, okay. And for this, so this cell has 3 neighbors, 1, 2, 3. So this cell become alive as per this rule, okay. Any dead cell with 3 live neighbors will become alive. So this cell become alive, so that's why its value is set to 3. Like this, we process all the cells in the board and update the next state. The output is expected to have only live or dead state. So we process the board again. We check whether the current state is live to dead. If it is true, then we set it to dead. And if this current state is dead to live, then we set the value to 1. So we change all the 2's to 0 and 3 to 1. Then finally we return this output. So that's what I have written here. First we initialize the rows and columns variable with the number of rows and number of columns in the board. Then traverse all the cells in the board. And if the current cell is live or live to dead, then we check the number of neighbors alive is less than 2 or greater than 3. If either one of them is true, then the live cell will become dead. So we set the state to live to dead, okay. And if the cell is dead, current cell is dead, and it has exactly 3 live neighbors, then we change the state to dead to live. So this is the first traversal of the board. Then once all the cells are processed and updated with states, then we process all the cells again and change the live to dead state cells value to dead, and also for the dead to live state cells value to live. So once we process all the cells here, the board will have either dead or live state as the value for all the cells. Let's look at the flowchart. Input for this procedure is a board with m by n grid cells. First we initialize the variable rows and columns with the number of rows and the number of columns. Then we start traversing all the cells. For each cell, we call update board function to update the state of the current cell. Let's take a look at the flowchart for the update board function. So input for this procedure is a board and the rows, columns, and the current row number index and the current column index value. Okay. So first we initialize the live count to 0, and then we initialize the neighbor offset array which has the offset for all the neighbors. -1, 0 is the neighbor which is present above the current cell, and 1, 0 is the neighbor which is present in the next row, and 0, -1 is the neighbor present in the previous column. 0, 1 is the neighbor present in the next column. These are all for the neighbors in the diagonal cell. So we traverse the neighbor offset array, and for each iteration we compute the index of the neighbor. Okay. So we add the current row number plus the neighbor offset, we get the current neighbor's index. Then we check the boundary conditions. So the computed value may be out of bound. So we make sure I is greater than or equal to 0 and I is less than number of rows, and j is greater than or equal to 0 and j is less than number of columns. Okay. So if it is within the boundary, then we check whether the cell is live or in a live to dead state. If that is true, then we count both the cases as live, so we increment the live count. So basically this for loop visit all the neighbors and compute the total number of live neighbors. Once the live neighbor count is computed, then we check whether the current cell is live. If that is true, then we check whether the live count is less than 2 or greater than 3. In that case, the live cell become dead. So we have to set the current cell's value to live to dead. Otherwise, we can skip that. And if the current cell is dead, then we check whether the number of neighbors live is exactly equal to 3. If that is true, then the dead cell become live. So we set the state value to dead to live. Okay. Otherwise, we just skip that update. So then the control will come back here, and for each cell this function will be called and the state will be updated. So once that is completed, then we will have to replace all the live to dead cells state to dead and dead to live cells state to live. Okay, because the output should have only two states, dead or live. Okay, so that's what this nested for loop is doing. So it traverses all the cell, it checks whether the current cell's value is live to dead. If that is true, then it changes the state value to dead. If the current cell's state is dead to live, it sets the state to live. It repeats for all the cells and then finally we return the output. Let's move on to coding. First I define the constants for the 4 possible state of each cell: dead, live, live to dead and dead to live. First I initialize the rows and columns variable with the number of rows and number of columns of the board. Then I write the for loop to process all the cells in the board. Update board function is called for each cell. So this will update the state of the current cell with respect to depending on the neighbor's state. Okay. And in the second nested for loop, I change the state value of the cells which are in live to dead state and dead to live state. If the current cell's state is dead to live, then I set this state of this cell to live, and if the cell's state is live to dead, then the state will be set with dead state. So we do this because the expected output should contain only either dead or live state. Next I'm going to write the update board function, which takes the board matrix and the number of rows, number of columns and the current cell's row index and column index. First I initialize the neighbors offset array. basically this array contains the offset of the neighbors with respect to the current cell. For example, the -1, 0 is the offset for the neighbor which is present in the previous row in the same column, and 1, 0 is for the cell present in the next row in the same column, and 0, -1 is for the cell present in the previous column and the same row. So likewise for the diagonal cells also we come up with the offset value. Totally there are 8 neighbors, so there will be 8 offset value in this array. Then I initialize the live count to 0. So in this for loop I compute the row and column index of each neighbor for the current cell by adding the current cell's row index and column index with the offset values. So I add r plus offset of 0 and j equal to c plus offset of 1. Next I check the boundary condition. So the computed index, if it is within the board's boundary, then I check the state, otherwise I skip that entry, skip that neighbor. So if that neighbor is either in live state or live to dead state, then I count that as live. Then I increment the live count. Once calculated the number of live neighbors, then I check whether the current cell is in the live state. If that is true, then I check whether the live count is less than 2. In that case, the current cell state will be set to live to dead. Else if the live count is greater than 3, in that case also the live cell will die. So I change the state to live to dead. If the current cell state is dead, then I check whether the number of live neighbors is exactly equal to 3. In that case, the dead cell become live. So if the live count is exactly equal to 3, then the current cell states changes from dead to live. Next I am going to run the test cases. All the tests passed. Next I am going to submit this program. Cool, this program is accepted. Next I am going to do the code walkthrough with sample input. We are given a 2x2 board and the expected output is with all ones in that board. Okay. So first we initialize the rows and columns variable with the number of rows and number of columns. So in this case 2 and 2. Okay. Then we traverse each cell and then we make a call to update the current state. So in this for loop we visit each cell in the matrix and update the current state by calling the update board function. So in the inner loop 0th iteration we process the top left cell. We make a call to update board function. So it computes the offset of each neighbors of this cell. Okay. So by adding the row offset and column offset value. So for example, if we add -1, so this cell's row index is 0, column index is 0. So when we add 0 to this number, it is -1. That is out of bound. Okay, so that's why we check the condition here only if the computed value is greater than or equal to 0 and less than the number of rows, and j is greater than or equal to 0 and j is less than the number of columns. Okay, but in this case it is out of bound, so we skip it. We skip the top neighbor. Okay, so likewise we keep computing the neighbors row and column index, and then we check the value, the current state. If it is live or if it is live to dead, then we increment the live count. Okay, so when we process this, so when we check this neighbor state, this is 1, which is live state, so we increment the live count. Okay, and so basically for this cell there are 2 live neighbors, so in this case it can continue to be alive, and in this case there are 2 live neighbors, so it remains alive. So this cell has 2 live neighbors, so there is no change in this cell state. But for this cell there are 3 live neighbors, so this dead cell become alive. So that's why dead to alive value is set to this cell. Okay, and after processing this cell we complete the traversal of all the cells. Okay, then we come to second nested for loop. Okay, here we traverse all the cells and check whether that cell's value is equal to dead to live or live to dead. If it is dead to live, we update the state to live. Okay, for this cell both the condition is false, then we go ahead and process the next cell. So for this also both the conditions are false, and this also both the conditions are false. And finally when we come to this cell, it is dead to live state, so we update the state to live, so it changes from 3 to 1. Finally we return, and that is an expected output. Next I'm going to do the time and space complexity analysis for this solution. The time complexity for this procedure is order of m times n. Basically we do the time complexity analysis in terms of the number of write operation. So for this input, this for loop performs 2 by 2 iteration, and in each iteration it makes a call to this function where we check all the neighbors in this for loop, which runs always 8 times. So that's why the first for loop performs 2 times 2 times 8, 32 iteration, write operation. And in the second for loop we do this write operation is done in the worst case 2 by 2 times. Okay, so totally it is 36 times. Okay, so if the number of rows and column is m and n, then the first for loop performs m times n times 8 write operation. The second for loop performs m times n operation. So the total number of write operation will be m times n times 9. So we remove the constant factor out. So time complexity is order of m times n. Space complexity is order of 1, because we are not allocating any additional space. We just use only these 2 variables. So that's why the space complexity is order of 1. Thanks for watching this video. Have a great day.